Imagine standing in an open field. The sky abruptly turns a bruised greenish gray. The ambient breeze drops to a dead calm, leaving total silence. Then an immense, twisting pillar of air rips down from the clouds, bridging the gap between the sky and the earth. Inside that vortex, wind speeds can range from a violent 50 kilometers per hour to an extreme 480 kilometers per hour, capable of lifting cars straight into the air. The window between these first visual cues and total impact is incredibly narrow, often leaving only seconds to react before the funnel touches down. How do entirely invisible atmospheric conditions suddenly combine to produce the most violent windstorms on the planet? Nowhere on Earth experiences more of these violent storms than the United States. The vast majority of them touch down in a specific central corridor known as Tornado Alley, encompassing states like Texas, Oklahoma, and Kansas. This region sits directly in the crosshairs of two competing climate forces. First, warm, moist air constantly pushes northward from the Gulf of Mexico. At the exact same time, cold, dry air sweeps down from Canada, violently colliding with that humid southern air. The specific geography of North America creates a natural atmospheric bottleneck, forcing these opposing air masses to mix and form the ultimate laboratory for extreme weather. When those two contrasting air masses collide, they rapidly generate massive, highly unstable cumulonimbus clouds, the towering thunderheads associated with severe storms. Inside these storm systems, we find a phenomenon called wind shear. This simply means that winds at different altitudes are blowing at completely different speeds and in different directions. This intense variation in the wind rolls the air into a highly energetic invisible tube that spins horizontally, perfectly parallel to the ground. As the thunderstorm intensifies, powerful columns of rising air surge upward through the cloud and catch the center of that spinning cylinder. The sheer upward force pivots the horizontal vortex entirely on its side, standing it upright into a vertical, rotating column of immense pressure. At this stage, it is still just a funnel cloud. The system only crosses the threshold to become a confirmed tornado at the exact fraction of a second it makes contact with the Earth. Every tornado is the culmination of a precise, sequential chain reaction of fluid dynamics and thermal energy. This chart shows the Enhanced Fujita, or EF scale. It categorizes tornadoes from EF0 to EF5, correlating estimated wind speeds with their capacity to destroy. At the top of that metric, an EF5 tornado packs enough kinetic energy to shear modern, strongly reinforced houses cleanly off their foundations, reducing these entire structures to nothing but splintered debris. The most terrifying manifestation of this power occurred in 1925 with the Tri-State Tornado, a colossal system that carved an unbroken 300-kilometer path through the American Midwest. It claimed hundreds of lives and entirely erased whole towns from the map, leaving behind empty fields where thriving communities had stood just minutes earlier. The EF scale maps the exact threshold where human engineering meets its limit against the raw force of atmospheric physics. But we are no longer completely blind to these storm systems. We can now observe them before they strike. Today, research meteorologists deploy specialized, heavily armored vehicles directly into the path of severe weather, gathering high-resolution data right from the core of the storm. This ground data is paired with modern Doppler radar, a technology that bounces radio waves off raindrops to map wind speed and direction. This allows scientists to detect the telltale signature of a rotating vortex high up in the clouds, long before a funnel ever drops. By identifying that rotation early, meteorologists can broadcast advance warnings, buying civilians the critical minutes they need to retreat into underground storm cellars or interior windowless rooms. We lack the power to stop the collision of warm and cold air masses, yet by decoding the mechanics of how a tornado forms, we turned one of nature's most lethal mysteries into a calculable and ultimately survivable threat.